Hey guys, hope you guys are doing well. Today, what I wanted to do is go over our Unit 7 AP Calculus BC study guide. This is at the end of Unit 7. We've covered everything. This includes everything but 7.1 of our lecture. Today, we're going to go over a few problems from each of the sections just to make sure you guys have everything down. We're going to start off by going over partial fraction decomposition, generally resulting in one or two LNs at the very end. We're going to go over distinct linear partial fraction problems where you have two distinct linear fractions. We're also going to go over L'Hopital's a basic problem where you guys have a couple of instances where you have to perform L'Hopital's rule, and then where you need to rewrite the problem before you can actually move on. As for improper integrals, we're going to go over some basic rewrites where we have to rewrite the integral. Then we're able to go through and take the integral. Sometimes we're going to find that it's divergent or convergent, and in a few of these, we're going to have multiple discontinuities. Okay. At the very end of this, I've added this a little bit later, we're going to go over integration by parts. Okay, so without any further ado, we're going to go over some basic partial fraction decomposition. The first thing you guys have to know in each of these problems is we are going to go through and we have to factor the denominator. So the first thing we do when we do partial fraction decomposition is we are going to go ahead and factor the denominator. And so what's going to end up happening is we're going to have x plus 2 over x times x plus 5. Each of these two terms have an x in common, so we're going to factor out an x, and that's where that comes from. The second step of this is we need to go through and we have to actually do the partial fraction decomposition. Partial fraction decomposition. After we're done with this, we'll go back through SIT-ION. We're going to go through and then we're actually going to integrate after we go through and rewrite this. And we're going to rewrite this as a over x plus b over x plus 5. It doesn't matter which order you go in, but once you find your a and your b, you have to make sure to plug it into the right spot. And from here, what we're going to do is we have to multiply everything through by the denominator. Step 3. We want to multiply each term by the denominator. When we do this, what's going to end up happening is our denominators are going to cancel and we're going to get some distinct terms. These terms are then going to allow us to solve for the coefficient of x and for the constant that we're given here. You guys will see what it looks like in just a moment. When we do this, what's going to happen is our x's cancel, our x plus 5's cancel, and we're left with x plus 2 on the left-hand side of the equation. On the right-hand side, x is going to cancel in this equation, and then we're going to distribute a, and we're going to get ax plus 5a. And on this case, we're going to cancel out the x plus 5, so we're just going to be left with bx. Okay. Now, what we're going to do is we're going to group our like terms together, so it's a little bit easier for us to see. So we're going to go through and group our like terms. And we're going to get x plus 2, our two like terms. We have two of these x's, ax plus bx. We're going to put a parenthesis around it. Plus 5a is our only constant. Okay. From this, we're going to factor out a x. From this, we're going to factor out an x, and we're going to have x plus 2 equals a plus b times the quantity, and we're going to be left with 5a. And what this is going to allow us to do is set up a system of equations, and this system of equations is going to allow us to solve for both a and b. First off, a plus b is equal to the coefficient that's in front of x, which is 1. A plus b equals 1. And on the other side of things, we're going to have 5a is equal to our constant 2. So we're going to be left with 5a equals 2. Now we can do solve for a, plug into the other equation. That's exactly what we're going to do. We're going to divide both sides by 5. We're going to get a equals 0.4 or 2/5. We're going to take and we're going to substitute this in here for a. We're going to get 0.4 plus b equals 1. and then we're going to subtract 0.4 from both sides, and we get b equals 0.6. Okay. You can, of course, leave this as fractions, and what's nice about this is going to allow us to go through and actually integrate. The problem with it before is it doesn't fit any of the other forms. We have to go through and we have to do this. Let me go ahead and add a page so I don't run out of room. And so when we do this, we're going to have the integral of a over x, which is going to be 0.4 over x, plus 0.6 over x plus 5 dx. Okay. If you're uncomfortable with this, we can split this into two different fractions where we're going to pull out the 0.4. We're going to get 0.4 times the integral of 1 over x dx plus 0.6 times the integral of 1 over x plus 5. Now, each of these fit the form of u prime over u because the derivative of the denominator on each of these, the derivative of the denominator in each of these is 1, which each of them now have 1 on top. So on this left-hand side, we're going to get 0.4 times ln of the absolute value of x. We have to put the absolute value there because this function right here, ln, is only defined for positive x values. It looks something like this. You have a vertical asymptote that comes through. It's just a quick sketch. It's not meant to look perfect, but we need to make sure that's positive, so we have to make sure to put an absolute value on our x. Okay, plus 0.6 times ln of x plus 5, and the same thing in this case. Because x plus 5 can be equal to a negative, we have to make sure we always put an absolute value on it. Plus c. That's it. Okay. As for the next thing I wanted to go over a couple L'Hopital problems with you guys. This is where we take the limit, and this limit is going to give us an indeterminate form. So let's go ahead and take a look at number 6 here. What's going to end up happening is we're taking the limit as we approach 0 from the right. Okay. So what we're going to end up doing is we're going to just directly substitute. See if we can get away with doing that. We get e to the 0 minus 1 plus 0 over 0 cubed. It's going to give us 1 minus 1 over 0, which is indeterminate form. Because of that, what we have to do is we then have to use L'Hopital's rule. And when we do so, we're going to take the derivative of the numerator, and then we're going to take the derivative of the denominator and write it out. The derivative of e to the x is e to the x. The derivative of negative 1 minus x is negative 1 over 3x squared. Okay. We're going to go ahead and try it again. We're going to try to direct substitute into this. We're going to get e to the 0 minus 1 over 0, which is going to give us 1 minus 1 over 0, which is 0 over 0 once again. Because it's indeterminate form, we're going to go through and we are going to use L'Hop's rule once again, L'Hopital's rule. And we're going to end up with, in this instance, the limit as x approaches 0 from the right of e to the x over 6x. Now, what's going to end up happening when we plug in 0, we're going to end up getting e to the 0 over 0, which is going to end up giving us 1 over 0. And as you guys know, when we get a number over 0, this means that we are approaching infinity. If you guys would like to look at this, we can always take a look at the graph of it just to see. So let me go ahead and go to Desmos with you guys. What do I have on Chrome? Okay, well, let's go through this. Let's go to Desmos, graphing calculator. Let's go ahead and type this in, e to the power of x, e to the power of x minus the quantity of 1, is it 1 minus x? 1 plus x. Okay, 1 plus x. 1 plus x. The entire quantity here divided by x cubed. Okay. And now, when we're looking at this, we're looking at it from the right. And if you guys notice, as we're coming from the right, this is approaching positive infinity. Our function's just going to increase without bounds. And so if you come from the right-hand side of the graph, you guys will see that it goes towards infinity as well. All right. that's that. Okay, let's do another one. Let's try out 9. Okay, number 9 is fairly similar. We do the same thing, plug in. We can't plug in infinity. We have to ask what happens. Well, as x approaches infinity, x cubed approaches infinity, infinity cubed, infinity. As for e to the power of infinity divided by 2, we're going to get e to the infinity, which is going to approach infinity. So this is going to end up with something like infinity over infinity, which is an indeterminate form. Because of this, we have to go through and do L'Hopital's rule. And we're going to end up getting the limit as x approaches infinity of 3x squared over e to the x over 2 times 1/2. Okay, we're going to end up getting the same thing. This is going to approach infinity over infinity, which is indeterminate form. So we have to use L'Hopital's rule again. And we're going to get the limit as x approaches infinity, not 0, infinity. We're going to get 6x over e to the x over 2 times 1/2 times 1/2, or 1/4. Okay, and unfortunately, we're going to have to do this one more time because it's going to give us infinity over infinity again. If you notice, e overpowers it. So we have to do L'Hopital's rule one more time. L'Hops. And we're going to end up getting the limit as x approaches infinity of 6 over e to the x over 2 times 1/2 times 1/2 times 1/2, or 1/8. It doesn't matter. And if you guys look at this, we're going to get a number. We're going to get 6 over infinity, which is going to approach 0. Okay, so that's it. All right, let's keep going at that. This is another problem. This is a nice problem. This is a problem that may or may not be on my test. This is a problem where when we go through and we direct substitute, but we can't direct substitute with infinity, it's not a real number, we're essentially going to get infinity times ln of infinity, and this is going to be an indeterminate form as well. What this means we have to do is we have to go through and rewrite the problem, and we have to try to put it in some form where we have a p of x over a q of x. We need to have something that looks like this before we can do L'Hopital's rule. P of x over q of x. So let's go ahead and try that out, and let's see what happens. I know that I can divide by the reciprocal of something. So I'm going to rewrite this as ln of x, and then I'm going to take and divide by the reciprocal of x over 1, or 1 over x. If I do this, I'm going to go ahead and do the same thing. Ln of infinity is going to approach infinity. 1 over infinity is going to approach 0. So I'm going to have infinity over 0, which is another indeterminate form, which means I can now go and use L'Hopital's rule. What I'd like to remind you guys is 1 over x like this we can rewrite as f of x, or in this case q of x, equals 1 over x, which is equivalent to x to the negative 1 power. So when we find the derivative, we're going to get negative 1x to the negative 2, or negative 1 over x squared. Okay, so let's go ahead and do L'Hopital's rule again, L'Hopital's rule. And we're going to end up getting the limit as x approaches infinity of 1 over x divided by negative 1 over x squared. Now, for me, I'm going to go through and rewrite this just because I don't want to deal with it. I'm going to have 1 over x times negative 1, or negative x squared over 1. When I do this, one of my x's is going to cancel. I'm going to be left with x to the power of 1. So I'm going to take the limit as x approaches infinity of negative x. Okay. If I do this, this is going to approach negative infinity, which means that the function diverges. Okay. All right. Well, the limit diverges. Okay. So what we're going to do is we are going to go down and try an improper integral. We're going to do one of these. Let's go ahead and I guess we can go through and do number 16. Number 16 here. Let's go ahead and try it out. We're going to go and first identify that one of the limits cannot be substituted into this function. So we're going to start off by rewriting this as the limit as x approaches, or in this case, let's call it a approaches 0, of the integral of a to 5 of 10 times 1 over x dx. What this is going to end up doing is when we integrate, we're going to get the limit as a approaches 0 of 10 ln of the absolute value of x evaluated from a to b, or a to 5. Okay. Let's go ahead and substitute this in and find f of b minus f of a. So we're going to get the limit as a approaches 0 of 10 ln of 5 minus 10 ln of a. Okay. All right, now here's the thing. When we go through and we do this, this first part is simply 10 ln of 5 minus 10 ln. And when we do this, we're essentially approaching 0. What ln of a does when we approach 0, you have to know what ln looks like. Okay. If we're approaching 0, you guys know this is what ln looks like. So let's go ahead and draw it out. Ln is going to look something like this. So from the right-hand side, this function is going to be approaching negative infinity. From the left-hand side, it's not going to be approaching anything. So the limit, we can't even take the one-sided limit when we're doing this. As we go towards 0, from 0 to 5, we're coming from negative infinity right here. Our y value is negative infinity, and we're going all the way up to 5 here. Okay? All right, and so because of this, we're going to get an undefined value. Once again, the limit does not exist at 0. So this is going to be undefined. Okay? All right, now if we were taking the limit from the right-hand side, we would say it's negative infinity, but still not a real number. So we'd run into the same issue. Okay? All right, so let's go ahead and go down. We're going to do an integration by parts problem, then we're going to call it a day. Let me go ahead and pick one we haven't done from class. I guess we could do this one right here. What you want to do with integration by parts is you guys want to go through and pick a u, and you want to pick a dv, and you're going to want to take the derivative of u, and you're going to want to integrate dv. You want to pick the integral to be something you know the integral of, and you want to pick v, something that's going to disappear and you don't want. Since we don't want to integrate ln, we're going to make u ln of 3x, and we're going to make x to the power 5 dv. And what we're going to end up doing is we're going to take the derivative of both sides of this, and we're going to end up getting du equals u prime over u, which is going to give us 3 over 3x dx. And on the other side, we're going to integrate, and we're going to get v equals x to the 6th over 6. Okay. And so on this left-hand side, these 3's are going to cancel, and we're going to be left with du equals 1 over x dx. Okay. All right. When we do integration by parts, we want u times v minus the integral of v times du. So let's go ahead and plug everything into this. So u is going to be ln of 3x. V is x to the power of 6 over 6 minus the integral of x to the power of 6 over 6 times 1 over x dx. So what's going to end up happening is one of our x's is going to cancel, and we're going to be left with x to the 5th. In the meanwhile, I'm going to factor out 1/6, and I'm going to have ln of 3x times x to the power of 6 over 6 minus 1/6 integral of x to the 5th dx. And what's going to happen is just integrate, and then we're done. So I'm going to get ln of 3x times x to the 6th over 6 minus 1/6 times x to the power of 6 over 6 plus c. And that's all she wrote. If you guys want to combine the 6's, go for it. I'm happy either way. All right, guys, have a beautiful night. I hope this was helpful.